Hi, my name is Winsa, and today I'll be explaining the fourth assignment of my computer system design class. So this is the debugger macro that I made, URDebug, and since a macro is just like a function, I store the R0 to R12 and LR register onto the stack, and the SP, LR, PC, and CPSR of the point right before the debugger call is stored into R9 to R12. This .ltort is a directive that I use to solve the invalid literal constant problem. And R7 is used as a counter that checks which register is being printed, initialized to 0. Okay, in here, this block of code just checks if the x50 is empty. And R6 is initialized as 0, which will be used as a shift amount, so we can get 1 byte of data from the register value. And in here, this block of code just updates the value of R8 register depending on which register is being worked on. So if R7 is less than or equal to 12, we know that we're working on register R0 to R12, which we get the value from the stack. Okay, if it's 13, it's we're working on stack pointer, and we know that the value is stored in R9. Same goes for the LR and PC. After that, we move on to the format. Since I want to keep this format right here, we want to print R0 space equals space before we print out the register value. So I store the ASCII value of R onto R2, and R4 holds the address for the URTXRX50. So I store the R in the TX50, so it will print out R in teraterm. And the next is the number right beside R. We check if it's a 2-digit number. So if it's a 2-digit number like 13, it will print out 13. If it's not, it will just print out what's stored in R7. So this block of code does that. And we want to print out the space equal space. So I initialized R2 and R3 register as the ASCII value of space and equal sign, and I shift this through this code block. So next we want to print out the value stored in the register. So since we have the value here, R8, we moved it to R3. We shift R3 by R6, which is the shift amount, initially 0. We mask the first byte, or the most significant byte. Then we move we shift this value R3 to the right by 28, so we get 1 byte of data in R3. And we want to convert the byte to ASCII, so we want to check if it's a number on alphabet. So if it's less than 10, we know that it's a number. If it's greater than or equal to 10, it's a alphabet, and we convert it respectively. We increase the shift amount by 4, so that if you want to access the next byte, we shift left by 4 bytes, so the most significant byte would be the second byte. And we store that in R4 to print it out, and we repeat this process until all bytes of the register value is printed. Then after that, we want to print out comma and space. We achieve that through here, right here. Okay, next, if we look at the format right here, after printing out 4 register, we want to go on to a new line. So I check if R7 is equal to 3, 7, 11, 15. So every time it's equal to that number, we just print out the next line right here. If it's not, and we just check if R7 is equal to 16. Okay, but if it's not equal, branch not equal to 2 backwards right here. So we check again if R7 is less than or equal to 12 or not, and we repeat the process until we're on the 16th, R7 equals 16, or if we're working on the CPSR register. If we compare R7 and 16 and they are equal, we know that we're working on CPSR register. So we want to print this out. So we branch equal to 6 forward. The 6 forward should be right here. So we want to print out CPSR space equal space. That is achieved through here. We just load the ASCII values of CPSR and the space and equals and achieve that through here. Okay, and the next important part is the first 4 bits of the CPSR register. So the NZCV flags, and we just use the AND operation to check if negative flag is set or clear. If it's set, we want to print out capital N. Not, we just want to print out small letter n. Same goes for the ZCV flags, and we do that by loading the ASCII values of n, capital N and small n. Okay, and we just print it out here. So in this example, N is clear, ZC is set, V is clear. Okay, on to the next, the IF bits. It's the same thing, same logic as the NCCV flags. We just use the AND operation to mask out the I bit. If I is set, capital I is printed. If I is clear, small I is printed. Same goes for the F. Next, we check 2 bits, J and T bit, and we get the J and T bit through here. And if we want to compare R1, we store the J and T bit into R1 and we check if it's 0, 0. So if J is equals to 0, T is equals to 0, we want to print R mode. J is 0, T is 1, thumb mode, and etc. So the R1 is loaded with the address of R mode, which is this defined right here. So the ASCII R mode, so we want to print R mode. So this block of code does that. So if R1 is initialized with the address, we want to print that out in here. Okay. And the next one is the current mode of the CPSR. It's the same thing, but we want to check the last 5 bits of the CPSR register, and we update R1 with the address depending on the CPSR mode, and the ASCII is defined right here in the CST ASM file. So it will print current mode equals USR. So it will print until this point right here. So after updating it, we want to output the CPSR mode right here. And after doing this, we want to print out the CPSR register value. So we move R12, which is the CPSR register, to R8, and we branch to 4 backwards. Yes, and this will output the data 1 byte at a time. So the CPSR register will be printed. After printing all the bytes of the CPSR register, we will branch 1 forward, so it will branch to here. We compare R7 to 16. Since we're working on CPSR right now, it will be equal, and it will print the last parenthesis right here. And after that, we move down here, and since we're at this point, we want to go to the next line. We just print the next line right here, and we load R1 register with the end line. So I wanted to keep the format right here, so it will print this line right here. So R1 is given the address to end line that is defined right here. Okay, then it will branch to 9F, 9 forward. So 9 forward, we just print the end line right here. Then to keep it format, from this point we want to go to the new line right here. This line, this code line prints that. After printing out the new line, we want to exit the debugger, and we want to restore all the original register values. So we subtract stack pointer with 52, so we can pop out the registers. And CPSR is updated with the original CPSR, which is stored in R2. After that, we just use the LDMIA, so we can pop out all the register that we pushed in the first debugger call. Then after that, we have the end of macro. This is what my debugger macro does. Now I will show real time how the debugger works when I try to run it inside the sorting algorithm. So the UART is initialized. I moved 32 to R1, so it will be updated here. R0 is the address of input data. R6 is the address of output data. So at this point, this is what the register looks like, and this is what the UART debug should print out in the iterator. And after UART debug finishes debugging or printing out everything, this register retains their values. So let's try to run this. Okay, so the UART is done printing it out, and I can see that the registers at this point was properly printed out here in the iterator, and I guess all the registers retain their value after running the debugger. Well, except for PC, because it went to the next instruction after running the debugger. So let's try to do the second debugger. Okay. Okay, the UART is done printing it out, and before we ran this debugger, we updated the value of R2 with 0 and updated the value of R5 with 1. So in the previous one, R2 was 1, and R2 is updated to 0, so R2 becomes 0 and R5 becomes 1, initially 1A, but because of this line of code it became 1. So the debugger macro works, and it did retain all the values of the register. So the debugger does its job without breaking the integrity of the registers.